In the early 20th century, scientist Albert Einstein discovered new information regarding light and waves. After the discovery, Einstein wrote to many of his colleagues about his recent work on relativity and the photoelectric effect to share his new ideas and findings. The photoelectric effect overthrew many of the classical theories which maintained that light was just a wave and helped cement the foundation of the quantum mechanical revolution.
Albert Einstein, a famous scientist, is well known for his brilliant contributions in the field of physics, and in particular, famous for his theory of relativity. The accomplishments of Albert Einstein are many and varied. They range from discoveries of the mysteries of the universe to being a promoter of peace and freedom. Einstein proposed that light comes in bundles of energy, called photons, that obey Planck's hypothesis of energy, which is the light of frequency consists of photons with an energy given by the following relation: E equals to h times f. E is the energy of the radiation, f is its frequency, and h is Planck's constant, 6.63 times 10 to the power of negative 34 joules times seconds.
In Einstein's photon model, a beam of light is a beam of particles, each carrying the energy hf. If the beam of light is more intense while keeping the frequency the same, the result is that the photons are more tightly packed. As a result, more photons pass a point in a certain time so that the photons shine on a given surface, increasing the energy. Einstein applied his photon model to the photoelectric model, in which a beam of light hits the surface of a metal and releases an electron. The minimum amount of energy necessary to eject an electron is called the working function of W. If an electron is given the energy E by a beam of light that is greater than W, then the energy converts into kinetic energy. The formula is K max equals E to E minus W. K max is the kinetic energy, E is the photo energy, and W is the work function.
American physicist Robert Millikan received the 1923 Nobel Prize in Physics for his work on the elementary charge of electricity and on the photoelectric effect. After a 10-year program of experimentation, in 1915, Millikan devised a system to verify Einstein's theory. Inside a glass bulb, a plate of surfaces of alkali metals such as lithium, sodium, or potassium was mounted on a wheel which moved past a knife and then into the path of the light beam at various frequencies. Millikan measured the voltage required to prevent the induced current. The graph of light frequency versus voltage was a straight line. The linear increase in the kinetic energy shows that the ejection is proportional to frequency. The slope of the curve is Planck's constant of proportionality. Einstein's equation was verified.
At the time at which this experiment was made, this prediction was as bold as the hypothesis which suggested it, for at that time there were no experiments available whatever for determining anything about how the positive potential voltage is necessary to stop the discharge of negative electrons from under the influence of monochromatic light varied with the frequency voltage of the light.
Throughout his life, Millikan remained a prolific author, making numerous contributions to scientific journals. He was not only a scientist, but his religious and philosophical nature was evident from his lectures on science, religion, and books.
A thorough understanding of the photoelectric effect has helped spawn many useful implications in our daily lives. For example, you have probably went into an elevator or a garage as the doors were closing. These systems work by using a beam of light and a device called a photocell. A photocell usually consists of a vacuum tube with two electrodes. The electrodes are two metal plates or wires. One electrode consists of a metal, the cathode, that will emit electrons when exposed to light. The other electrode, the anode, is given a positive electric charge compared to the cathode. When light shines on the cathode, electrons are emitted and then attracted to the anode. The current that flows from the cathode to the anode can be used to open a door or to ring a bell in an alarm system. Photocells are commonly used in factories. Items on a conveyor belt pass between a beam of light and a photocell. As each item passes the beam, it interrupts the light and the current from the photocell stops. As a result, a counter is turned on. With this method, the exact number of items leaving the factory can be counted. Photocells are also installed in light poles to turn the street lights on and off at day and night. In addition, photocells are also the basic unit in solar energy panels that convert some of the energy in the light into electrical energy.
The phenomenon was significant in the development of modern physics because of the questions it raised about the characteristics of light, such as particles versus wave-like behavior. The effect remains important for research in science of areas, as well as forming the basis for a variety of useful devices.